Hi, today we're going to continue on looking at some limits and some properties of those limits. So, like I mentioned, we're starting off with some properties of limits. So, assuming that we have a limit of f of x as x approaches a and a limit of g of x as x approaches a, where they both exist and we have c as a constant term, we have a limit of c times f of x as x approaches a is equal to c times our limit of f of x approaches a. So essentially, if we have something like this, we can factor out our c, find our limit of f of x, and then multiply it by our c value. Now, if we have limit of f of x plus or minus g of x as x approaches a, that's going to be the exact same as if we take our limit of f of x as x approaches a and add or subtract our limit of g of x as x approaches a. Now, if we have a function where we have two functions multiplied together, so for limit of f of x times g of x as x approaches a, that's going to be equal to our limit of our function f of x as x approaches a times our limit of g of x as x approaches a. Now we have a quotient version of that one as well, because if we have limit of f of x divided by g of x as x approaches a, that's the same as our limit of f of x as x approaches a divided by our limit of g of x as x approaches a, where we have a restriction that our limit of g of x as x approaches a cannot equal 0 because we cannot divide by 0. We also have an exponential limit. So if we have limit of f of x to the power of n as x approaches a, that's the same as our limit of f of x as x approaches a to the power of n. And then we have a radical version. So if we have a limit of the nth root of f of x as x approaches a, that's the same as the nth root of our limit of f of x as x approaches a. So we'll do an example about how one of these can be utilized, and then you can essentially extrapolate it to other practice questions. So for example, calculate the following limit. So we've got the limit as x approaches -2 of 3x squared plus 5x minus 9. So we can use our addition and subtraction property to simplify this. So this is the same as the limit of 3x squared as x approaches -2 plus our limit of 5x as x approaches -2 plus our, actually in this case it'd be minus our limit of 9 as x approaches -2. Now we can also use our constant part of that. So if these constants being multiplied in front can move in front, so that would be the same as 3 times our limit of x squared as x approaches -2 plus 5 times our limit of x as x approaches -2 minus our limit of 9 as x approaches -2. Okay, so that gives us 3 times our limit of x squared as we approach -2 would just be -2 squared, so 4. Then we have 5 times our limit of x as x approaches -2, so that's just going to be -2. Minus our limit of 9 as x approaches -2. This doesn't have a variable in it, so it's not going to change at all. So -9. So that gives us 12 minus 10 minus 9, which tells us our limit is equal to -7. Now, what you would have noticed here is essentially the limit in this case, because we're approaching an x value that wasn't a non-permissible or a place where we're changing functions, was the same as if we had just plugged this in for our variables. So that brings us to our direct substitution property, which states if f of x is a polynomial or rational function and a is in the domain of f of x, then our limit of f of x as x approaches a equals f of a. So the key thing here is a is in the domain of f of x, which means that a is not a non-permissible value of, say, a rational function. If that's the case, our limit of f of x as x approaches a is just going to be the same as f of a. So if we look at this one, where we want to calculate the following limit, and we've got limit of 3x plus 1 to the power 5 as x approaches 2, we can see that this is not a rational function, so we don't have to worry about a non-permissible value. So we can just go directly to that substitution. So this would be the same as 3 times 2 plus 1 to the power of 5. Now 3 times 2 is 6, plus 1 gives us 7, so this would be the same as 7 to the power of 5, which is 16,807. Now we also have what's known as a limit of indeterminate form 0 divided by 0 for rational expressions. So this is when, as we approach our specific a value, our numerator and denominator both approach 0. So when we have this, what we want to do is factor the numerator and our denominator, and then cancel any common factors. And then we can essentially use our substitution property. So for example, we want to evaluate our limit of x squared minus 16 over our limit, or sorry, over x cubed minus 64 as x approaches 4. Now, what you'll notice is when you substitute 4 into our numerator, that's going to give us 16 minus 16, which is 0. When we substitute 4 into our denominator, that's going to give us 64 minus 64, which is 0. So that's this case of 0 divided by 0. So first thing I want to do is factor this. So our limit of x squared minus 16 over x cubed minus 64 as x approaches 4 is the same as our limit as x goes towards 4 of this here is a difference of squares. So that's going to be x plus 4 times x minus 4. And this is a difference of cubes. So this would be x minus 4 times x squared plus 4x plus 16. Now what we'll see is this term would essentially cancel out with this term. So now that's leaving us with a limit as x approaches 4 of x plus 4 over x squared plus 4x plus 16. What you'll notice is it's no longer 0 over 0. So we can substitute in our 4. So this would be equal to 4 plus 4 over 4 squared plus 4 times 4 plus 16. That gives us 8 over 48. We can reduce that, and our limit is equal to 1/6. Okay, so this is what we do if we have a limit of indeterminate form 0 over 0 for a rational function. We also have a rule for if we have radical functions. So with this, we want to multiply the numerator and denominator by our conjugate. So essentially, we want to create a difference of squares. And then we'll go through and cancel any common factors. So for example, we evaluate, and we have a limit of x over the square root of 9 plus x minus 3 as x approaches 0. So I'm just going to rewrite this. So I've got the limit as x approaches 0 of x over 9 plus x in our root minus 3. So we want to multiply by the conjugate of this radical. Now, in some cases, our radical will be in our denominator. Some cases, it will be in our numerator. Whichever one it is in, we will multiply by the conjugate of that. So the conjugate of this would be root 9 plus x plus 3. And we want to multiply the numerator and denominator by that. So in the numerator, I can see things aren't really going to cancel out, so I'll probably just leave it as x times the square root of 9 plus x plus 3 divided by, when we FOIL this out, we've got root 9 plus x times root 9 plus x, which will give us 9 plus x. Because it's a difference of squares, our middle terms will cancel out because we're going to end up with 3 times root 9 plus x and negative 3 times root 9 plus x. So let's just cancel out. And then we've got negative 3 times positive 3, so that's minus 9. You'll note that we have positive 9 and negative 9, so let's cancel out. So currently we have limit of x of our function as x goes to 0 of our function x times root of 9 plus x plus 3 divided by x. What you'll notice is we can also cancel these x's. So now we have our limit as x approaches 0 of the square root of 9 plus x plus 3 And you'll notice here I made sure I put brackets here because if I didn't put these brackets, we'd only be looking at the limit as this part approaches 0. Now in this case, because this is just plus 3, it probably won't make a difference, but we could in some cases have variables in both these terms. So now that we've got to this, we can just use our direct substitution property. So this is just going to be our limit of the square root of 9 plus 0 plus 3. Now, if the square root of 9 is 3, then we have plus 3. So our limit as x goes to 0 for this function is going to be 6. Okay, now something you haven't seen before, something known as the greatest integer function, also known as a floor function. Now, if we have square brackets around something, so square brackets around x represents the greatest integer that's less than or equal to x. So therefore, if we have this example, so we have a floor function of 4.9, our biggest integer that is less than 4.9 would just be 4. Same as this one, floor function of 12.9 means we're looking for the greatest integer less than 12.9, which is going to be 12. Once again, floor function of negative 1.4, which would be our greatest integer that is less than negative 1.4, which would be negative 2. And then we have a floor function of negative 5.9, which would be negative 6. Okay, so now we'll talk a bit about limits of reciprocal functions. To find the limit of a reciprocal function, we look at our limits from the left and right sides as we approach a non-permissible value. We, however, may also be asked to find only the left or right side limit. So for example, if we had the limit as x approaches 0 from the positive side of 1 over x, then we're looking for when we have 1 divided by 0 from the positive side. So that means we're going 1 divided by something infinitesimally small, but the positive version of it. So that's going to give us positive infinity. Where if we do the same limit, and sorry, this should have been from the negative side, as we substitute in our 0 from the negative, we are all of a sudden dividing by something infinitesimally small, but it's negative. So 1 divided by something very small, negative, would give us negative infinity. Now we can see that these don't match each other. One's positive infinity, one's negative infinity. So we can say it does not exist. Now, if we have our limits for 1 over x squared, now we're, say, going from a positive side, then we're looking at 1 divided by 0 as we approach 0 from the positive side. So once again, something infinitesimally small, but positive. When we square it, that's still going to be infinitesimally small, but positive. So 1 divided by that will take us to positive infinity. Where if we are approaching from the negative side, we're going to have something that is infinitesimally small but negative. But when we square it, that's going to get rid of that negative. So we'll have something very, very small and positive. So 1 divided by that will take us to infinity. So these match. So we can say our limit is equal to infinity. However, we can also say it does not exist because it does not equal one particular value. Okay, so for example, we want to find these following limits. So we have our function 1 over x plus 2. We're going to find our limit as we approach -2 from a positive side, and then we'll look at our limit as we approach from the negative side, and then look at our limit overall. So this would be the same as 1 over -2 from a positive side plus 2. So from a positive side, this would, for example, be, say, -1.999, which when we add to 2, is going to give us a positive value, although infinitesimally small. So therefore, 1 divided by something infinitesimally small and positive is going to give us positive infinity. Now this one, we've got 1 over -2 from the negative side plus 2. So for example, if we say from -2.0001 plus 2, that's going to give us a negative very small number. So 1 divided by that is going to give us negative infinity. Now, because these did not equal each other, our limit as we approach -2 does not exist. Okay, next we've got our limit of 1 over x squared minus 9, and we're going to look at approaching it from the positive side of -3, the negative side of -3, and as a limit as we approach -3 in general. So this would be the same as 1 over -3 from the positive side squared minus 9. Now, if we're approaching -3 from the positive side, so we're not quite -3, so when we square it, we're going to end up with a number that is less than 9, but very close to 9. So when we subtract 9, we're going to end up with a negative value that's very small. So when we take 1 and divide it by a negative value that's very small, that's going to give us negative infinity. Now, if we look at this one, where we have 1 over, and then we've got x squared, so -3 from the negative side squared minus 9. From the negative side, we'd be at something that's slightly less than -3, which when we square it will give us something larger than 9, which will give us a positive down here. A very small positive, 1 divided by it will give us positive infinity. So therefore, we can say this one does not exist.